So this is going to be the third of our little spring break plus more review, just to make sure we kind of get back into the swing of things here from where we left off. We're going to be talking about composite shapes, area of polygon, and area of sectors here. Again, this is all stuff we kind of talked about before the break happened, but we're just going to kind of review here just to get ourselves back on track. So we're going to start with composite shapes. And what composite shapes are basically what I call them Franken shapes for Frankenstein, because all you're doing is really putting two shapes and stitching them together. Like, for example, this weird shape right here, that's made up of, if you cut it like this, it's made up of a rectangle stitched together with a triangle. Now, there are more ways you could cut this up too. I mean, you can cut it up like here and make it a parallelogram in a triangle. But again, that's one way of cutting it up. Same here. Again, you can cut it like this, and you have a triangle stitched together with a square. Some of you might find something like this. You know, you cut it down the middle, and you have two trapezoids that are stitched together. So these are, again, they're polygons, so you could also call this a 1, 2, 3, 4, 5. So this is a pentagon, but it's also a composite shape because you can cut it into smaller shapes that are kind of building blocks. Usually rectangles and triangles are the ones you're looking for because those are the smallest shapes you can get, but there are other shapes like trapezoids and kites and stuff you might find occasionally too. So the way you get the area of these shapes is you simply, like we just did, cut them into shapes you know how to do, and then add the areas together. So let's say this shape right here. This kind of, you have this little triangle at the end here, you have kind of a rectangular body, and you have this second little triangle at the end here. You also have kind of like this trapezoid looking shape right here too, if you want to do it like a trapezoid. But I'll do it a little bit more piecemeal just so you can kind of see the process. So what I would do is I would say, okay, let's cut this down the middle here, and cut this into three problems. A triangle, a rectangle, whoops, a rectangle, and a third triangle, or a second triangle rather. Well, let's go ahead and find the first triangle first. So this triangle right here has a base of 5 and a height of 3. So we know that the area for a triangle is 1/2 base times height. So half 5 times 3, or 5 times 3 times a half, however you want to slice it. In this case, that would end up being 7.5. This would be meters squared. So that's the area of that first triangle right there. Now let's try to find the area of the rectangle. Now, the reason I did it like this is because you have to kind of think, all right, to get the area of the rectangle, I need its base and my height, which is not necessarily the numbers listed because I'm not going to use 15 and 18 because 18 goes all the way to the end here. I don't want that piece right there. I want the entire length here. So I want 15, not times 18, but 15, which takes care of the top base, times 5, because 5 is the height. I wouldn't even do 15 times 18 anyway, because those are the two base, or those are both going the same direction. For a rectangle, you need a base and then a height in the opposite direction, not the same way. So I would be using 15 and 5 as my two numbers, because that's my baseline and my height line that form the rectangle. So 15 times 5, which would give you 75 meters squared too, if you want to label it as you go, which is fine. And then thirdly, we get this last little triangle here. So that has, now remember, this right here is a height, so it's perpendicular. So that means I have a height of 5, and I want this base right here. Well, if this base is 15, and the entire thing here is 18, that means from here to here, that has to be 15. So this piece right here has to be 3. Now again, it's not drawn to scale, so some of you might be saying, well, that clearly looks bigger than the 5. Well, again, it's not drawn to scale, so you can't make that assumption. So 3 here, 15 there, for a total distance of 18. So this triangle is also going to be 1/2 base times height. So, whoa, let me try that again. There we go. So 1/2 base times height, which is 7.5 meters squared again, same as the first triangle. So now, to get my full area, I'm going to add them. 7.5 plus 75 plus 75, or 75 plus 2 7.5s, really doesn't matter. So these two together make 15, and 15 plus 75 would give me a grand total of 90 meters squared. So again, the whole idea here is that I have 3 individual smaller shapes that I find individually, and then add them all back together at the end to get my area of the full shape. Again, you can also treat this as like one big trapezoid and do base 1 plus base 2 times 5 as the height, and then take half of that, and that'll give you 1 trapezoid plus 1 triangle, but you get the same answer either way. Let's take a look at a few more here. In this one here, we have a curved piece here. So if you ever have a curved piece, you're going to be looking at either a full circle, a semicircle, or a quarter circle. That's usually how it goes. So if I cut this like here, and again, the way you cut it is kind of up to you, but when I see this, I say, okay, there's a curved piece right here. So let me see if I can't slice off that curved section by doing this. That way I isolate that curved piece here. So I have all my curved section there. Excuse me. And then I'm left with a rectangle on top and a rectangle to the side, which I can easily deal with. So this seems like a good cut. I have 2 rectangles I know how to do. This right here is a quarter circle. So that's going to be, the area of a circle, remember, is pi r squared. And that's how you get a full circle. So to get a quarter of a circle, I'm simply going to divide it by 4, because it's a quarter of a circle. So let's go ahead and label these as shape 1, shape 2, and then shape 3 will be my circle, or my quarter circle. So for shape 1, it's a rectangle, so it's base times height. Well, 15 is my base, we'll say, or my height, doesn't matter. But what am I going to multiply it with? Because I don't know what this line right here is. Well, if I knew what this line right here is, that could help me. But I don't know what this line is. And this is where we have to kind of think about the properties of these shapes here. So for a circle, remember, all the radii in a circle are equal. So if this is my center of the quarter circle, that means this distance is the same as this distance, is the same as this distance, is the same as this distance. So all the radii of a quarter circle, half circle, full circle, they're all going to be equal. So this dotted line here is going to be the same as this dotted line here. And if you look, this dotted line here is going to be the same as this 8 right here, because they're both going the same distance, top to bottom. So that means that this dotted line is 8, which means that this dotted line is 8, which if you really want to, means that this line right here is also 8. So 8 kind of travels up and along the route here. So radii is 8, other radii is 8, which means this line right here is 8. So that'd be 15 times 8, which, if I just check my math here, 15 times 8 give you 120. So 120. The second one is pretty similar. It's just going to be 24 times 8, because my line right here is now 24, not 15. So we do that. 24 times 8, get 192. And then lastly, we have the quarter circle. Well, I just said that my radii is 8 from center to edge. Note, this is not the diameter, because even though it looks like a diameter because it's a quarter circle, if this was a full-blown circle, this 8 would only go from center to edge, not all the way across. So it'd be pi times r squared all over 4. Because again, it's a quarter circle. I wouldn't do this if it was a full circle. If it was a half circle, I only do divide by 2, right? So pi times 8 squared, which is 64. I just know what x squared is, so I just put it in 64. Then divided by 4, we get 50.27. 50.27. So now what we're going to do is take this answer and add it to these two numbers over here. So we're going to take 50.27 and add it to 120, which is our rectangle, and then add that to 182, which is our other rectangle, and we get 362.27. So 362.27 feet squared, by the way, if you label it. Again, even if you have curved pieces, you can still do this. It's just a matter of making sure you know when to put in the circles. And like I said, the most common types of circles we see are full circles, half circles, or quarter circles. Again, if it's a quarter circle or a half circle, just divide by 4 or 2 respectively, and you'll be fine. Make sure you remember to divide by 4 or 2 at the circle part, though. Don't save this to the end. You can't just divide by 4 at the end, because then you're dividing everything by 4, not just the circle part. So divide by 4 in the formula for the circle, and then add it together at the end. Adding everything together should be your very last step. You shouldn't have anything left to do after that. Over here, again, we can cut this up in quite a few different ways. The way I see it here is that I have kind of a parallelogram on top. If I slice this top part off, there's a parallelogram, which I know how to do. That's base times height. I could cut this up into a rectangle like this and then have a trapezoid on bottom. Um, and I really don't want to work with trapezoids if I don't have to, though, because I really don't like the trapezoid formula because I have to add two bases together. So what I would do is I would just kind of contain this line down here and cut it like this. So I have one big long rectangle in the middle, that'd be shape 2. And I have this little triangle at the end here. Now again, if you want to cut into a trapezoid and use your trapezoid formula, go ahead. In fact, I encourage you to do it and see if you get the same answer I do, because you should. So this would be my shape 3 right here, which would be this small triangle. So shape 1, let's see here. Base times height, so that'd be 8 times 4. Base of 8, height of 4. Multiply those together, we get 32. Feet squared, again, if you want to label it. This rectangle right here looks to be about 20, not 15, because remember 15 goes from here to here and then stops. So this entire length is going to be 20 times my baseline like right here. I don't want the full thing, so again, I don't want 12. I just want from here to here, which I don't know. So I look up top. Well, I don't know that either, but I actually do. Because since it's a parallelogram, I know that this top piece, 8, is also going to be this bottom piece, 8, down here, kind of like this was with the circle there. Top and bottom of a parallelogram are always equal, which means that this bottom piece right here is also going to be 8. So again, use the other shapes and use their properties to help you out. Always remember that opposite sides are congruent in a rectangle, a parallelogram, or a square. And then always remember that radii in a circle are all congruent in every direction. So this second shape there is going to be 20 times 8. Okay? 8 is my base, 20 is my height. And again, the reason I got this 8 here is because 8 on this line means 8 for this base here because it's a parallelogram. It means 8 down here for this second piece. So 20 times 8, which is 160. And then to finish it off, this triangle. So I need a base and a height. Well, I have this line right here, which I don't know. Let me do it in a different color here. So I don't know what this line right here is going to be. But with a little thinking, I can figure it out. If this full line right here is 20, that's 20. And this line right here is 15. Well, that means that the rest of this has to add up to 20, right? If I contain this line down here, it should end up with 20. So if that's 15, that means the rest of it has to be 5. Because 15 plus 5 more would give me my full 20 there. So it's going to be 5 times something divided by 2. So I need to figure out the something. So I need to figure out how big this little piece right here is. Well, once again, if the full thing is 12, and this little piece right here is 8 from here to here, that's 8. That means from here to here has to be the rest of the 12, which is going to give me 4. Because 8 plus 4 would give me back to my 12. So it'd be, whoops, not 8, sorry, be 4. Which would end you with 10. So again, use the other shapes to help you figure out the missing pieces of your third shape or second shape. So now you end together 160 plus 32 plus 10 would all give you 6, 7, 8, 9, 10. So carry the 1, give you 202. Assume I didn't miss add or anything like that. So again, use the other shapes to help you out figuring out your measurements for the shape that you're on. Let's go ahead and continue out here. The other thing with composite shapes is that you're not always going to add. If they ask you for the shaded region part of problems, that usually means you're going to subtract, not add. So this case here, we have a circle that's kind of been cut out of a square, and it wants us to find out how much is left. So we have this region here, this region here. So it wants to find out all of these. Get a different color here. So it wants to find out the area of all these corners here. How big are those regions? Well, to do that, what we're going to do is we're going to take the area of the square minus the area of the circle, and that will give us the area of those curved pieces, of those triangle-looking things. So we have to first find the area of the square here, and it does say it's a square. So I know that if that's 28, that means that this is 28 as well because it's a square. So 28. So the area of the square, whoops, try again. Square is 28 times 28. So if we do that here, 28 times 28, we get 784. So now we need the area of the circle. Circle is pi r squared. Now this is where we have to be careful. We are not given the radius of the circle. In fact, we're not given anything about the circle. So I need to figure out how big this distance is right here. That's my r. I need to figure out how big that length is here. Once again, use the shapes around you to help. If this distance here is r, and I know that from top to bottom fully is 28, right? So from top here to bottom here, that's 28. So from here to here, 28. That means that this here has to be half that, which is going to be 14, because it's going from center to edge, not all the way across. So basically, the side of the square rather gives you the diameter, not the radius. So this is going to be pi times 14 squared divided by 2. And if we do that here, pi times 14 squared divided by 2, and we get 307.88. 307.88. Now, again, we're not going to add these together because we want to take the circle out of the square. So we're going to take 784 minus 307.88 and get our answer that way. So 784 minus 307.88, and that will give us 476.12. 476.12. Let me try that again. 476.12. There we go. So again, if they want you to find the shaded region of something, it's usually going to be a subtraction. If they want you to just find the area of the shape, it's usually going to be addition. Just for future reference here, some more subtraction problems. So if I want the area of just the shaded part here, again, I could try to figure out the area of each shaded region individually because they are shapes that I know how to do. But the easier thing would be to look at this as two problems. You have a big rectangle minus the two triangles, one going this way and one going that way. So if I take the rectangle minus both triangles, I can get the area of all the shaded region here. So let's go ahead and figure out the area of the triangles first. And now, since the bases are marked congruent here, we can kind of assume that the triangles are congruent because the bases are the same and their heights are the same too, because they both stop and end at the length of the rectangle here. So we can assume that both these triangles have the same area. So if I figure out one, I can figure out them both. So for the triangle, we have area equals base. So the base, we'll do this one over here. The base of this triangle is 6 yards. Times, well, how do I know the height of this triangle? So how do I know how tall this triangle is? Well, once again, the height of this triangle is basically the height of the rectangle almost. It goes from top to bottom. Well, what other line goes from top to bottom? Well, this 8 right here. It goes top to bottom. So, excuse me. So that means that this one over here too, because again, they're congruent triangles. They all have a height of 8. So it'd be 6 times 8 divided by 2, which is going to give you 24. And again, I'm going to times this by 2 because I have 2 of these triangles in here. So times 2, because I have this one and this one. So that's going to give me 48 as my subtracting area. So again, if you have triangles and another, or any shape rather, if you have a repetitive amount of shapes that are being subtracted, just go ahead and figure out one of them and then multiply it by however many shapes that you need. So in this case, I figured out one triangle, times it by 2 to get them both because they're both the same triangle. They both have the same base, same height, same triangle. Then I need the area of the rectangle, right? So this one's a little bit difficult to get. I know that the height is 8 because it goes from top to bottom here. The height is 8 yards. So 8. I need to figure out what the baseline is though. Well, I know that this right here is 18. I know that this length right here is 6. What I need to figure out is what's it going to be all together. So this is where it comes into a little bit of a tricky-ish situation. So if this right here is 6, and again, I should probably have marked these down here, but let's assume that this is a equal or a isosceles triangle so that these are congruent as well. Usually what happens here in these kind of triangles is that when you have a height, if it's an isosceles triangle, then the base here is split in half. So that means if the entire thing's 6, that means this little piece right here is 3, and this little piece right here is 3. Well, if these little pieces are both 3, look at how these are split here. From here to here is 3. Well, if we bring that up here, that's the same as going from here to here. That's also 3. So now I have what this little slice is here. Well, because this is a congruent shape here, that means this little slice right here, from here to here, is also 3, and then this part right here is also 3, because remember this base itself is 6. So to figure out my base here, I'm going to do 18, which is this distance, plus the 3 over here, plus the 2 3s, or the 6, over here. That will give me my full length. So 18 plus 3 plus 3 plus 3, essentially. So 18 plus 3 plus 3 plus 3 would give me 27. Again, a little bit of investigative work there because you had to make sure you remember that when you have a height coming down in an isosceles triangle like this, or basically in any acute triangle almost, when the height comes down the middle, it splits your base in half. So you have half of your base over here and half your base over here. So that's where I get this 3 and 3 from. So the 6 just gets cut in half, and then I have to kind of use my spatial analysis to bring that 3 up to make this line complete, essentially. So then that will give me 8 times 27, which would give me 216. So last little bit here is I take my 216, which is the area of the rectangle, minus 48, which is the area of both triangles, to get the area of just the shaded region. So 216 minus 48, which gives me 168. So again, the shapes you know how to deal with, just a little bit of prep work and making sure you know all the segments and stuff before you go ahead and try to solve the areas of them. This one here is very similar to the one we just did in the previous page. You have a circle being cut out of a triangle. So let's go ahead, and again, we know it's going to be taking the circle out of the triangle, so we have two shapes, a circle and a triangle. Let's go ahead and figure out the circle first, because that seems like it might be the easier one, because I know the radius. So it's just going to be pi times 6 squared. Now, I'm not going to divide by 2 here, or by 4, because it's a full circle, so I want the entire thing here. So pi times 36, which is what 6 squared is, gives me 113.1 essentially. So that's the area of the circle. Now I need the area of the triangle. Well, I know the base is 17, so it's 17 times height divided by 2, but I need to know what the height is. Again, this goes back to the fact about circles that the radius is all, or the radii are all equal to each other. So this is 6, this is 6, this is 6, this right here is 6, which again gives me some help here because, and again, I drew this in a very poor way. I apologize because it's not a line cut off. But this 12 is measuring from straight up to straight down. It's not measuring the actual slant. It's measuring from here to here. So this distance right here, that is 12. So let me kind of erase this little extra bit here. So that right there is meant to be my 12. So once again, I have 12 is from here to here. I have 6 is from here to here because the radii of those circles are all equal. So that means that my base, or my height rather, is going to be 18. Again, poorly drawn on my part. I apologize for that now that I look at it a second time. But that's what that line there was meant to convey, that the entire length from top to bottom is going to be 12. Or sorry, from top to center of the circle rather is going to be 12. And then you add the 6 extra down here because of the radii, and you get the full length, which is 18. So we do this here, 17 times 18 divided by 2, by 2, and we get 153. So 153, and then lastly we go ahead and do my subtraction. So 153 minus 113.1. You should never get a negative area, so that's why you always want to make sure you do the bigger area minus the smaller area, and we get 39.9. There we go. So once again, when you're dealing with these problems, take your time, piece out all the lines, all the segments you need first, and then do your areas once you have all your segments and stuff pieced out and you know all the tools you have to work with. And then last two things here, we have polygons and sectors. So a regular polygon is a polygon with all equal sides and all equal angles. So this would be an example of a regular polygon. If all these sides were equal, it'd be what we call a regular pentagon. Okay? So if I want the area of this, what I basically end up doing here is I basically divide this into a bunch of triangles. So triangle there, triangle there, triangle there, triangle there, and I count how many triangles I have, find the area of each of them, and then add them all together. Because again, these triangles should all be congruent because it's a regular polygon. And what that basically led us to figure out here was that the area ended up being one of two ways. 1/2 times A, which is called the apothem. So this line right here, it's not the radius because it doesn't go to a corner, but this line right here is called the apothem of the polygon, which means it goes from center to the edge of a side here at a right angle. So there's a right angle there. Times capital P, which is the perimeter. So this right here is the perimeter of the polygon. So you add up all the lengths all the way around. Or another way of saying this is 1/2 times A times L times N, where N here is the number of sides and L is the length of those sides. Oops. Ah, I hate when I do that. Let me try this here. There we go. So L is the length of those sides. So you can do either one. They're both going to give the same thing. Basically, P is what you get when you do these two together. L times N is the perimeter, essentially. So it's just a matter of how you want to write out your formula or think about your formula. But again, this only works for regular polygons. So if it's not a regular polygon, you can't use this trick because your triangles are no longer equal and you have to do a bunch of other stuff. But if it's a regular polygon, as long as you know this piece of information, you can solve it. So just do two real quick ones here. So this one right here, let's count the sides first. So 1, 2, 3, 4, 5, 6. So it's a hexagon. So what I would do is I would do 1/2 times my apothem, which is 8. So from center to edge, so that's 8, times my length, which is 12, times 8, or sorry, times 6, because 1, 2, 3, 4, 5, 6, because there's 6 sides. So this is my L, 12. This is my N, 6. This is my apothem, my A. So I go ahead and put this in. So 0.5, which is 1/2, times 8 times 12, times 8 times 12 times 6 gives me 288 square inches. Again, very simple formula, just multiplying stuff together. Just make sure you pick the right stuff. One way they can kind of muddle this up is to give you something like the second one here, where they don't give you the apothem, but they give you this little diagram in the center. And this is a case where you have to fall back on your Pythagorean theorem bit, because what you need to realize here is that, okay, this entire length here is 14, because if this is 14, all the sides are congruent all the way around. I should probably put doubles here, because I put singles here for each of these little small halves, so I'll put a double here to make sure I don't conveying the wrong message. So if each of these sides are 14 here, that means that this piece has to be half that, 7, because 7 plus another 7 would make it 14. So what I end up here in this little spot here is I end up with a triangle. I end up with something like this. 7, 24, and I want to figure out what this little apothem line here is. Well, this is a Pythagorean theorem problem. And you should note here that 24 is not a side, 24 is the hypotenuse because it's across my right angle. So what I would do here is I would do 24 squared is equal to 7 squared plus x squared. And then go through this like a Pythagorean problem. So this would be 49 plus x squared is equal to, and then if we do 24 squared here, 24 squared gives us 576. Then we subtract 49, 49, there we go. So minus 49, we get 527, 27 is equal to x squared. And so we don't want x squared, we want x, so we're going to square root both sides. And we get the square root of 527 gives us 22.96 essentially. 22.96, which I'm just going to round to 23 just to be, for simplicity's sake, as my apothem, my x. So this line right here is 23. So now I can go back and use my area formula. So now I have 1/2 times the apothem, 23, times my length, times the number of sides, which I just said was 1, 2, 3, 4, 5, 6, 7, 8. 8. Remember to not double count these as one side. These are both half of one side. So this entire thing here is just 1. So I have still a grand total of 8 sides. So we go ahead and type that in my little calculator here. So 0.5 times 23 times 14 times 8 sides, and we get 1288. So again, if you see a right triangle, don't be afraid to use Pythagorean theorem if you need to figure out like a missing piece like the apothem or even the base edge. Sometimes that does happen. And again, make sure you're using the apothem, not the other line. So sometimes they might try to trick you and do something like this. And they'll say that this line here is 10. And they're trying to trick you into using 10, not 8. But remember, still use 10 because, or sorry, use 8. Don't use 10 because 10 is the radius, not the apothem. Apothem has to go from center to the edge, not from center to corner. So you want center to edge, not center to corner. And lastly, we have the area of a sector. So a sector is a slice of a circle, and they usually give you two things about the sector. They give you the radius and they give you the degrees. So this is a theta here. We normally call this d rather than theta just because we use more appropriate lettering. So we'll put a little d here for degrees. So the way you get the area of a sector is you set up the following proportion. You have area of the sector. So this a here is area of sector. Okay. So this is the area. Let me write that area word a little bit better there. Area over pi r squared, which is the area of the full circle, is equal to degrees over 360. So this is the degrees of angle, or I'll say of sector. So that's this little angle right here. Again, don't try to memorize this just brute force and try to just repeat this over in your head. Think about what's going on here. I have area of the slice over area of the circle. Degrees of the slice over degrees of the circle. There's a format, there's a flow to it. Slice over circle, area over area, degrees over degrees. So again, you're comparing the ratio of the area it takes up to the ratio of the degrees that it takes up. But it's always the same format. Area to area, slice to circle. Degrees to degrees, slice to circle. So for instance, let's say they didn't want to do this problem here. Well, let's go ahead and set up my proportion. Area of the sector, which I don't know, so it's going to be my x. Usually this will always be your x, your area of the sector, because that's what I want you to find out. So area of the sector over pi times r squared, so 7 squared. Let me write that 7 a little bit better there. So pi times 7 squared over degrees, which is 50, because I have 50 degrees, times 360, or over 360. So what I would do here is figure out what this is. So pi times 7 squared, which is 153.93. Just to make sure I confirm that here, let me try this. Right, 153.93. So x over 153.93 is equal to 50 over 360, and then we just cross multiply. So cross. So this here would be 360x. Cross multiply over here is equal to 50 times this. So 153.9 times 50 gives you 7695. 7695, which sounds like a big number because it is, but remember we're going to divide this by 360 to get my x by itself. So it's going to be cut down by quite a bit. So divide by 360, and we get 21.375, which is a lot more of a reasonable answer. Meters squared. So again, area over area, slice over circle. Degrees over degrees, slice over circle. And once you get down to that step, figure out what your pi stuff is, get a single number there to make it easier on yourself, and then top times bottom, write down, top times bottom, write down, and again, there's going to be an equal sign in the middle. You don't make them into one fraction, you set them equal to each other. Over here, there's another trick that they play here, is that they give you this angle right here is 120, but they shade the other side. So what you want to do here is when you set up your fraction, let me do it over here. It'd be area of the sector over pi times 12 squared. That starts out normally. Here's going to be a 360, as it always is. This top number is not going to be 120, though, because I don't want this sector. I want this shaded sector over here, which is behind my angle. So what I want to do is figure out how big is this angle right here. Well, if this is 120, this green angle has to be 360 minus 120, which would give me 240. So I'm going to be using 240 as my angle, not 120. And again, the reason is because my sector is shaded with this angle in mind, not with the back angle in mind. So just be careful when they try to throw that to you and they shade the region behind the angle. You're not going to use the angle as your measurement. You have to do this little 360 minus 120 bit to get your angle, and then use that in your formula. Because again, a full circle is 360. So if I take away the 120, that means whatever's left has to be for this angle over here. So now we go ahead and do our cross multiplication. So multiply here, multiply there. Actually, I should probably figure out what this is first, shouldn't I? So let's do that. So pi times 12 squared is 452.39. So this right here is 452.39, and then now I can go ahead and cross multiply. So 360x is equal to 452.39 times 240 is 1085.73.6. 1085.73.6, which again, sounds like a big answer because it is, but we're going to divide by 360 here to get rid of it. And we get x is equal to whatever this is, 301.593 repeating. So 301.593 repeating. So again, nothing really big different with that one, but just remember that they can sometimes give you the opposite sector that they want, and you have to do that little 360 trick to go back and figure out what the angle is that you're actually going to be using. But it's probably one of the more or longer forms that we have. I wouldn't say more complicated because it is a very simple procedure, but it's a big chunky formula. So you can try to bull rush and bootstrap it and try to just repeat the formula in your head 10 times to memorize it, or you can kind of understand what's going on and using that to help you figure it out. And again, it's a simple format. Slice over slice, area over area. Slice over slice, or sorry, let me try that again. Slice over circle, area over area. Slice over circle, degrees over degrees. If you kind of remember that pattern there, then you'll always know how to set up your fraction, and you can solve it from there. Hope this helped you out. We might do one more kind of little review on word problems next time, and then we kind of get into the last little bit of material we didn't get to before spring break to wrap up this chapter. Hope you enjoyed the video. Have a good day.